because low materials and complex procedure of fabrications. We didn't need to concern about the trial expenses 200 years ago, but because it was very cheap. In modern process, rare elements or expensive materials are frequently used in the process, so we should worry about every choice. Okay, so all procedure of fabrication was drastically changed also. For example, there are at least 100 processes to make NAND memories. The research paradigm should be changed to the in silico approaches, which is based on the computer simulations. So what if we already knew about good starting points or origins of failure? Before perform the experiments, the simulation screens many candidates based on the theory and laws. I want to give you one example for this. In the field of polymer industry, particularly liquid crystal polymer, is Japan industry lead this market today. Many fellow companies want to make better quality LCP materials. However, it is impossible to follow up with companies through the Edisonian approaches because they already got a very nice and very good skill to make the LCP materials in Japan. But follow companies cannot through the Edisonian like general method. Okay, so we should introduce or find a better way. We believe in one of the best candidates is the in silico approaches, which is the computer-aided research. Many of us already knew about in silico approaches is the best candidate for reasonable and efficient R&D method. However, why people feel difficulty to adopt simulation on their research? Because there are too many barriers: expensive equipment, domain knowledge, and complex Linux environment. In order to perform simulation, we need to buy equipment, especially high-performance computer. It spent more than $200K US plus, we should pay for the maintenance fee every year. Not only this barrier, but also we should learn new kind of physical background. Maybe you are familiar with the physics or chemistry, but you should know about computational physics and you should know computational chemistry. It is very different story. Right? So last barrier is Linux environment. You guys may be familiar with the Windows or Mac environments. However, most of the computer simulations are working on the Linux environment. Even you don't have enough time to do your own research, but also do we should know about Linux? It's going to be very big barrier, right? So how can I solve this? Think about this. So I introduced the virtual lab with the virtual lab introduced the cloud-based simulation platform, MaterialsCare. MaterialsCare is the materials and chemistry simulation platform on the cloud. Customer could perform simulation modeling, calculation, and analysis at once. You don't worry about equipment, domain knowledge, and complex Linux systems. As you may well know, simulation has been used in many fields, such as semiconductor, and metal, ceramic, and polymer industries. I'd like to show you application for the semiconductor industries. So lithium-ion battery is a quite hot topic in semiconductor industry. You may design next generation battery, analyze for the degradation and charge capacity, voltage, and speed of, for instance. Not only battery industry, but memories, solar cell, even display industry frequently use the computer simulations. So in this point, I want to say a very success story in the field of the semiconductor in the virtual lab. Actually, this story is based on the virtual lab. It's one of customer stories. So in this case, in this customers, in these researchers, want to make or want to design the next generation memory, especially phase change memories. But the problem is that he got 29 dopant candidates. Yeah, here's the experiment, guys. Yeah, it takes around more than 6 months by experiment. So he should reduce time for the write papers, right? So at that time he decided to introduce computer simulation, and he want to help the virtual lab to introduce simulations. So we are introducing simulation to this experiment guy, and finally only 4 candidates left. Okay, and first time 29 candidates, but by using the computer simulation, it's only 4 candidates left. Finally, he successfully synthesized the phase change memory on using these 4 candidates. And he write a nice paper in this here. And this is, I think this is paper covers, I think. And look at this table here. Actually, this is not to scale, okay? So what if he only used the experimental case? He takes 180 days with 20 man-hours. He also needs huge space, like 5,000 square feet. Approximately, it costs 120 US dollars. Okay, but what if he introduced simulation? It only takes 2 days with 1 manpower, and there are very little space needed for the 250 square feet. Approximately, it costs 2,500 US dollars. Okay, this is a real story, and this is a really successful story in the virtual lab. So I'm really introducing for here. So what about metal and ceramic industries? Alloy or manufacturing process also adopt the computer simulation to improve performance and design. Many tools can be manufactured by ceramics. For example, cutting tools and brake pad and artificial teeth. Special artificial teeth is the kind of the zirconia, so it's very important which materials are good for mechanical properties and corrosion free. The last applications are chemical and polymer industries. In the COVID-19 situation, there are eco-friendly polymerize to be a big issues. By using computer simulations, you may design eco-friendly polymer with huge mechanical strengths. Besides eco-friendly polymer, there are many issues regarding the polymer industry. Elastomer, especially, is a tire industry here, and conducting materials and catalysis are very also important issue in this part. I will show you some example for the polymer properties calculation on material scale. Dimethyl terephthalate is the monomer produced by the decomposition of PET. So when you dispose of PET in the recycle bins, it is processed into the flake and converted to the BHET through the glycol and methanol decompositions process. It is quite important procedure in plastic recycling process. Every simulation starts from the modeling. In material scale, you draw monomer or polymer directly using Catcher or loading this open database here. You can use the open database here or directly drawing using Catchers. And next step is simulation setup, including calculation method and parameters. It's a little bit complex, but it is professional mode. So you may use the preset parameters according to your purpose. Okay. And last step is the analysis. You can connect the analysis module and calculation module to get results. You also get analytics, electronics, vibrational, and geometric properties here. So this is the kind of the surface analysis, and you can see the nice graphical user interface near the HOMO and the LUMO level here. Okay. And This part, I briefly demonstrate the phonon calculation of materials here. The procedures as follow. First, simulation model always start from the modeling. Okay. So next step is calculation setup, and last step is analysis. In the calculation setup, I gonna do the structural relaxation and phonon calculation, and in the analysis, I'm gonna show you phonon density of state and dispersion relations and the effective charge. Okay. So let's see how work in simulation on materials here. I will show you. Just a second, please. Okay, you can see my Chrome browser, right? So you can go to materialscale.com, mathcube.com, and I already logged in. Okay, so I briefly introduced the menu of this one, and we are consist of several menus: account, work, data, blog, documentations, and pricing, open research, and workshop. This is workshop here, right? So you can press the account. There are many information are included here. This is my ID here, and I use the many data in here. I already calculate almost 5,000 jobs in here. And if you want to buy credit, and you can use the buy credit tab, and billing method we are using here. And if you add some potential, you can add potential tab here. Then add and modify, and you can write the pseudo potential for the quantum espressos. And this is polymerize tab, and last one is a workshop. Okay. So let's start the simulation now. So I would like to go the work page and new work. Okay. Today I'm gonna a very short demonstration here. And I'm gonna make the simulation model for the silicon. Okay. There are many methods to build the silicon in materials here, but I'm gonna use the preset here. Okay. I preset, and I'm using the silicon and generate. Okay. Yeah, right. So there are many other things using, for example, manganese oxide, and gallium nitride, and copper, or anything else. And you can build the surface by using preset. There are many surfaces are here, and nanostructures, and organic molecules, and polymers. But I frequently use the database. Okay, this database is this is sourced from the materials here. And if you want to searching for the silicon, for instance, and I write silicon and click. And there are many silicon type in here. For example, this one or this one. And sometimes there is huge silicon. Maybe this is kind of some amorphous silicon or something like that. I'm not sure. And this is the symmetric group of PA3. And also there are CMCM space group with 12 atoms in the unit cell. They got 112, 20 volume in here. Otherwise, you can also find the titanium oxide here, for example, here. And you can use this one, PNMA structures, or something like that. Okay. Right. So back to the calculation. So I've done simulation modeling here. And after that, I'm gonna do the calculation setup for the structural relaxations. So click the simulation button and quantum espresso and general button. And you can see this method and connecting modules. There are about one available module to connect, and click the desired module at the navigation bar. Actually, this is a navigation bar. So if you want to connect the quantum espresso module, and structure builder, and you just click here. Okay, right. So this is, you can see the connect module Quantum Espresso and structure module, and you can see the dark blue here, and this is sky blue here. It means it has connected together. All right. So I'm gonna set up here by using the template, and I want to calculate relaxation. Okay, but phonon calculation should be very high. Precision is needed, so I'm gonna change the precision to high. And this model is work, right? And I'm gonna change the structure. I wanna do the structure optimization. So with the ionic and cell optimization, I select this one. And I said phonon calculation very accurate calculation needed, but most of parameters are set up by the high precision. So I'm gonna change slightly 50 cutoff and 400 cutoff low. And I'm gonna change the 20 by 20 by 20, something like this. Okay. And when you set up all parameters, you just write the, if you like the relaxation silicon, and press start job. Okay. When you press start job, is the calculation is started. So at this point, you're gonna pay for the computational research service. But start from the modeling, this is free, and this is the input script generating, also free. But you only pay for the calculation things. Okay. So you can check the status. Now name is Relaxation Silicon and Quantum Espresso. And server is we use the 48 cores with the one node. And this status is prepare stage. Okay. So I'm waiting for the few minutes. It's gonna be finishing. So I already calculate for this one. And with when you finish the calculation, the green message is coming out here, like a successfully finishes, and this is your low data. When you press here, and you can check your input file, or it's standard out files, or some it's memory uses here, and there are many things. Okay, so if you want, you can check the data, low data. But when you finish the relaxation, we're gonna do the phonon calculation, right? So I want to change this name also to relaxation. This is actually step 1. Okay. So, and this is the actually also workshop. Silicon phonon. Okay. And I want to connect one more module for the to calculate the phonon calculation. I'm gonna press simulation and Quantum Espresso and phonons. And actually, you can see that this method here, there are 2 available modules to connect. But materials can strongly recommend the structural relaxation before phonon calculation, right? So you can directly connect these structures, but this is not fully relaxed, not a ground state structure. So we strongly recommend the relaxation structures, okay, with the phonon calculation. I'm gonna connect this one, and you can see the sky blue here and dark blue here. So I'm gonna change it to the converters, right? It is okay. And also, where is this one? It's electron phonon coupling, but I don't know electron phonon coupling. So you can press here. This is metal only. So I cannot calculate silicon because silicon is not metals. Okay. Oh, the electric constant effective charge, this is for non-metal. Okay, right. I'm gonna calculate this one. And phonon calculation. And when you calculate the more this accurate calculation, you can increase grid. But I don't want to take a long time, so I just use default value. And I want to also use post processing for the band structure and density of state. Okay. And in here, the crystal system is automatically assigned because the silicon is the basically FCC structure with the diamond structures. So FCC is automatically selected for the high symmetry point. So this is the default value. But if you like to change the value, and you can change like here. Or Dasio state, this is the grid for Dasio state. So I don't want any changes. So, and then press the phonon and silicon. Okay, press start job. It's done. So you can see the here is the phonon silicon with the 48 CPU with the prepare, and this is realization is running, right? So I think it takes a few minutes when we finish it. So when you finish the phonon calculation, you can see this window here. And when you finish calculation, you can check the green text successfully finished, and you can check the first one is the dielectric constant effective charge. And dielectric constant is kind of matrix in here with in the Cartesian axis. Then you can check the dielectric constant, and this is diagonalized composites. And also you can check the effective charge in the Cartesian axis for the each atoms. And this diagonalized composition is the same. So it means this material is not anisotropic, but isotropic. Okay. So, and you can press post-processing. We calculate the band structure and density of the right. So you can check the gamma points to X to K and gamma. This is actually high symmetry point. And you can see the two of those, actually 6, right? But it's only, you can see the 2 of those. But maybe one of those is behind here. So this is the acoustic branch, and this is the optical branch. So, and you can check the band crossing here, and density of state, phonon density of state here. Okay. So this is a short demonstration of material scale. I get back to my presentation. So second, please. Okay, right. So I summarize simulation modeling first step, and next step structural relaxation, and third step is phonon calculation, and finally you can get a band structure and density of state and dielectric constant and effective charge. Okay. So next, there are few competitions all around the world because materials and chemical computer simulation is still blue oceans, I think. Sorry. So materials design and Synopsys are big company in this field, but they did not provide a cloud HPC or consulting service. Also, you should pay for the entry cost and annual license fee in here. But, oh, sorry. However, you don't worry about these kind of things in materials care. You only pay for the service, meter-based pricing, and I will let you know more details about pricing model of materials scale next page. So you only pay for the computer research, computing resources usage, basically 25 cents per CPU hour, and you don't need to pay for the simulation modeling or analysis, as you know. Virtual Lab also provides a thermodynamic database with very small price, it's 1 cent to $1. It depending on the which database you want to use here. And commercial version or some free version is here. And last one is the machine learning based polymer prediction models. Actually, this is the collaborate with the Memorize in US company, which is founded by the Professor Lampi, who is associated with Georgia Tech, and Dr. Chiho Kim. So we are collaborating with Memorize in this module. It's a machine learning for the polymer. And this is the subrection model, and it depending on the how many properties polymer you want to predict. So 1,500 to 5,000, it depends on here. And this is bulk package. You may get a maximum 50% of through this. And actually, there are many customers concerned about pricing, right? So because they don't know how much should pay for each calculation, so Virtual Lab released the unlimited plan. And using this plan, you don't worry about pricing if you subscribe unlimited plan. And actually, the most striking features in Virtual Lab, we provide professional supporting plan. So customer always face to trouble with simulations. Of course, it could be, right? So professional consultants who are doctoral degrees always ready to help them. There are two kinds of plan, pro and business version, depending on the frequency submitting and supporting areas. Last part is just pricing sample. So when you're doing the structural optimization, it's around the $1 to $10, it depending on your system size. For example, you want to calculate the optical properties, it's around the $3 to $10 at average. But maybe it's gonna be very big system. It's gonna be takes more money for that. And we also provide the molecular dynamics, classical molecular dynamics by some LAMS. EOS is very cheap calculation because just to finish the calculations, and it's under the $1. And tensile test, cascade, dislocation, and melting and quenching, molecular dynamics. And very recently, we released the polymer molecular dynamics simulation. And you can please check the polymer molecular dynamics in MaterialScale also. And yeah, that's almost finished here. This is traction and performance of Virtual Lab. Virtual Lab is more than 7,000 users with the different 67 nations. Also, many university and national institutes in the MaterialScale. And you may know the UC Irvine here and University of Tokyo and Korea Institute of Science Technology, which is the biggest national institute in Korea. Actually, I really want to list up for the industry, but it can be due to the NDA. Anyway, there are several big industry in Korea and US working with the virtual labs. And this is our traction, but maybe you are not interested in traction. I'm gonna pass through here. So I have mentioned previously, I have a lot of trial and errors to marketing strategies. Here is an example of one of the most successful marketing activities, this workshop, okay? So I'll summarize again in the closing remark, but it's quite impressive for us. This workshop to be held from the May 28th, 2000 this year, it's Korean time, to today. So today is last workshop day, So through this workshop, more than 8 times the new user inflow was achieved. In addition to this international workshop, we are continuously researching effective marketing tools. This is milestone for the 5-year-old Virtual Lab. Virtual Lab has successfully developed the inorganic materials and organic molecules and polymer simulation platform. From the first quarter of 2021, we are going to start biomaterials such as new drug simulation to the second quarter of 2012, 2022. And finally, Virtual Lab believe that all engineering R&D environment can be integrated in MaterialScale. We will try to make real R&D square. This is our team. We consist of 17 members, including 5 PhDs. The business area is a web-based simulation platform. It's quite unique and transparent. We believe in that the most powerful thing in Virtual Lab is team building. Also, one of the more important things, we know cutting-edge simulation technique and have domain knowledge such as physics, chemistries. That is why we are going to change the research paradigm shift to the platform. I think this is the most important part. Why Virtual Lab? Virtual Lab always try to find the companions to change the research paradigm. So I'm pretty sure that Virtual Lab has a strong team. They got not only strong domain knowledge, but also mature experience. Second, Virtual Lab is unique and transparent. No one could succeed on cloud-based simulation platform in the world. Virtual Lab will do that. Virtual Lab is open-minded, so we are going to expand in bio, medicine, even food research areas. Summary here, this is the Virtual Lab value propositions. Virtual Lab provides the state-of-the-art materials and chemical simulation on cloud. Anytime professional consultant are ready to support your researches. All right, thank you so much. Lastly, Virtual Lab create a new paradigm of scientific research via cloud and platform. Thank you so much, guys.
All right, thank you very much, Minkyu, for your very nice presentation and nice overview of Virtual Lab products and services. And of course, I invite everyone here who is attending today's workshop to try our services and to visit our website. So at this point, yeah, I propose that you take a quick look at the Q&A section. Although at this stage, I cannot see any direct questions.
Yeah, I have one question, but it just it's not related to my talk, so I just pass the answers. Okay. So if you have questions, just contact us to the Virtual Lab via email or some support that in email address here. And if you have questions, just please email me. All right. Yeah. Thank you so much.
Right, yeah. In that case, if there are no more questions, I propose to move straight into the next talk or next presentation in today's episode of the workshop. So our next talk will be given by Dr. Fedor Gumans, who is Chief of Marketing and communication and business development at SCM. So SCM is a Dutch startup company active in computational chemistry and material science. So Fedor Gumans so originally studied surface science and theoretical chemistry, and then joined the SCM as a business developer in 2012. So Fedor mostly enjoys discussing with researchers worldwide how computational chemistry and materials modeling can help tackle their problems and advance their research in many different application areas. And he therefore has been very active in developing the business model aspects of SCM and as well as actively participating in marketing events and in other kinds of say business workshops dedicated to promoting the commercial development of SCM. So SCM is mostly known for the ADF, modeling suite, so Amsterdam Density Functional Theory. And it's actually a company which I personally know quite well since I did some work for them as a freelancer quite a few years ago. And they've been actively involved in EMMC activities. So EMMC is European Materials Modeling Council. And this is another organization with which I'm collaborating at the moment. So Fedor, if you can hear us, welcome first of all. And at this stage, I propose that you start your presentation, and you're now ready to present. So welcome, and the floor is yours.
Okay, well, thank you, Gabriela, and thank you for the invitation to give my view on commercialization in materials modeling and the platform aspect of it in particular. Let me start with sharing my screen and then go to presentation mode. So, good morning, good night, good evening for those in Europe. So my name indeed is Fedor Gumans. I'm with software for chemistry and materials. And in the introduction, I would like to give you a little bit of background of where SCM, Software for Chemistry and Materials, comes from. So how we actually started off as a company, how we managed to sort of maintain a useful business model for us, and what we envision in the future. And as you've seen in the talk by Dr. Minkyu Park, of course, a lot of the future modeling activities will be on platform-based simulations. So cloud computing, web-based interfaces are all going to become much more important. So I have a little bit of thoughts on that later on as well. What I will start off with is a couple of case studies specifically related to modeling OLED materials, because that is one of the application areas where we managed to serendipitously actually find good business value from some of the aspects in our software, and we're still actively developing in that area, but then getting more into multi-skill modeling as well as platform-based type of simulation, which enables researchers much more quickly to develop a new set of materials relevant for the entire OLED stack. And then I think in the end, I will have a little bit of more time left. I can discuss how that extends to other type of materials as well, in particular for batteries, polymers, and catalysts. But let's see how we get along. And let's get started. So from the user perspective, why do you want to use materials modeling? Perhaps I'm preaching to the choir here, but by using modeling and simulation, you can greatly reduce the time and costs you need to develop new materials. And as I will show in a slide later on, a lot of this has to do with density functional theory becoming a very pragmatic method to get properties out of your simulations, which are at least in the right ballpark. And as you can see in this slide over here, in this graph over here, right around the onset of density functional theory becoming more popular, especially in the chemistry community, people actually started using these calculations in patent claims to back up experimental results, and also being able to cover a larger range of compounds in their IP claims. And in a nutshell, there's essentially two ways in which modeling can help you at the moment, which is by brute force virtual screening. So this is known as forward prediction, and a lot of activities going on in terms of machine learning and materials informatics to do inverse prediction. Again, more on that later on. But you input a material, out comes the predicted properties as you've just seen. The other way in which modeling and simulation can help you is by understanding why a particular molecule or material gives you a certain type of property, helps the researcher more quickly think about better ways to even improve the material or molecule properties that you're after. So those currently are the two most interesting modes in which you can use modeling and simulation to advance your research and development. And so if you think about any device that people would have in their pocket, for instance, a cell phone, there are, of course, a lot of different materials in there, each one of which are continuously being improved and further developed. So if you think about the batteries that go in these cell phones, of course, we want to be able to talk for longer, use our internet for longer. So we need better batteries, and we don't want the phone to be too heavy. So we need lightweight materials. We don't want them to catch fire, so they need to have stable electrolyte solutions. These are all kind of properties that you can model at the atomistic level. And by doing the modeling, you can decrease the search pace for new and better materials. Similarly, for the chips that go in there, so the central processing units, they need to get more power packed in them whilst keeping small at the same time. So a lot of materials development is going into building better chips. All these again ultimately relate to atomistic behavior. So through modeling, you can understand how you can make materials that have a better IV profile. Also, how to make them using etching and deposition processes. And obviously, a very important aspect of these telephones is the screen, which is going to be the main part of the talk. So how do you develop better OLED materials? And a very important aspect of that is the color of the pixels that you have in your screen and the lifetime of the OLED materials. So let's dig into that later on and think about how modeling can help you develop these new materials more quickly. So from our perspective, we develop these computational methods. So we've been developing density functional methods for 5 decades now, as well as a number of other atomistic methods more recently that help you do this forward prediction. Input a material or molecule, output a certain property. And more recently, we've been integrating these with higher range methods that allow you to cover the multi-scale range, so mesoscale methods as well as continuum methods. From our perspective, as you've also heard in the previous talk, I think it's very useful that if you're running these calculations, that you have access to excellent technical support. So in our company, we have around 15 developers who actually write the code, and these are the people that also help you if you have any problems. We don't do so much on consulting, so we do have a couple of support scientists who can do consulting, but our goal, our business model is to have the end user use the software themselves, and we're happy to help them get over the barrier, and we provide support for that. But in the end, we want people to be able to run the simulations themselves. And more recently, and faster and faster, I would say there's some interesting new developments in the space of using machine learning in the context of materials, so materials informatics, if you will, which allow you to even faster make your new development cycles. Right, okay, so then going back to the company itself, we're based out of Amsterdam. In the 70s, Professor Evert-Jan Barends started his PhD, and he started writing what was the first density functional theory code for studying chemistry, for studying molecules. And at the time, DFT was kind of well used in the physics community, but the chemists didn't like it. They thought it was a weird theory. But at that time, it was the only way you could actually calculate reactivity and spectroscopic properties of inorganic molecules, which you couldn't dream about by using proper, as the chemists call it, proper ab initio methods. And so Evert-Jan started discretizing these methods that were used for bulk properties. And that first code, Amsterdam Molecule, was actually very useful to understand chemical reactivity. And that attracted interest from companies in the Netherlands, but also in Japan, that wanted to use these calculations to understand the chemical reaction pathways, and from that develop better catalysts. So in the 80s, we had researchers coming from Japan, but also from the Dutch companies, Shell, Akzo, and Unilever. They would come to the theoretical chemistry corridor. They would sit down, look at the punch cards, and see how they could actually run their calculations and use that to their advantage to make better catalysts. And so around that same time, we also started implementing a periodic variation of that Amsterdam density functional code. It's called BAND, and it was different from the physics code because it uses atomic orbitals, and that enables you to study surfaces as proper surfaces. And so in those 80s and early 90s, we managed to keep developing and supporting these density functional codes, but Evert-Jan realized, together also with Tom Ziegler, who was actively developing and promoting these density functional methods, that in order to be able to keep a sustainable business model where we can have people develop and support the software, it would make sense to start licensing the software, so ask people for a contribution to continue using it. And so in 1995, we started as a spin-off company, starting with one person and roughly growing one person every year. We're still based in the Free University in Amsterdam, where we rent space, but we're completely independent. But we like the environment because we have a lot of good collaborations going on with all-term collaborators and new collaborators in the theoretical chemistry group. I just wanted to highlight again this graph here, where we have the number of patents and the number of articles where density functional theory is used. So as you can see, there's a good correlation. And as you can see, that correlation in papers with DFT in chemistry starts, as I mentioned, somewhat in the mid-90s. And this is when Tom Ziegler and a couple of others started actively pushing DFT as the pragmatic way to understand chemical and atomistic properties. And so there's a famous paper from the 1993 where Tom pushes this forward, and also in 1993 there was the infamous Becker-3-Lip paper from the Gaussian group where they mistreated the original implementation, but this has been the default for a long time. For organic chemists, luckily, we have a lot of better exchange correlation functionals available. But I think those set of developments, so in the mid-90s, really triggered the community to use these density functional based methods to study and understand chemistry. So roughly 15 years ago, we also started implementing different methods. So away from density functional theory, going to less accurate but faster methods. So density functional based tight binding. There's reactive force fields. Together with Albemarle and DSM in the Netherlands, we implemented our version of COSMO-RES, which is a continuum based method using activity coefficients you get essentially from DFT calculations that allows you to calculate thermodynamic properties in solution. And the last couple of years, we've been more and more involved in European Union projects where we collaborate with larger companies and universities to make new technology from the universities available for the end users in industry. And so the industry perspective, so if we think about commercialization, is that they do like to have some sense of stability. So if they use an open source package, they need to make sure that they can run the same calculations 20 years down the line. And so these open source packages, they need to have a beefy enough community to make that happen. Or they want to go with commercial software where they know if a company has been around for long enough and there's healthy growth, that they can continue to use that software. And also, of course, they get access to more premium support as they would get from, let's say, a user forum from an open source software. Okay, so currently we have around 25 people, and so this was us over a year and a half ago, just before we weren't allowed to be together in such large groups, and maybe after summer we can be again. And as you can see, we're having 15 scientific software developers. Most of them have their PhD in computational physics or theoretical chemistry. And I think that's a major asset because these are the people that help you with any problems or questions that you may have. Right, so this is just reiterating the methods that we have in the Amsterdam Modeling Suite. So we have a bunch of atomistic methods centered around ADF, still our flagship product. And we don't have much in the mesoscale ourselves, but we're filling in those gaps through multi-scale modeling collaborations, as we'll get to that later on. We also focus on making it, let's say, easy to deploy. So there's a graphical user interface, there's a Python interface if you want to do some scripting, build your own workflows and do high throughput screening. We're definitely moving into the cloud, but from our current perspective, there's not that much use case for that yet at the moment, but we're cloud ready. But we still need to make the graphical user interface a little bit better usable from that perspective. But you can use the graphical user interface locally and then submit calculations to Amazon. All right, now let's go to modeling OLEDs. So organic light emitting diodes essentially are a stack of materials where, let's say on the top at the cathode, we start injecting electrons that meet holes that come from the bottom, so they come from the anode. So we need to have good mobility of those holes and electrons, and then they meet each other in the middle in an emissive layer. And a lot of research activity is on finding the best emitters. And so the first generation of these OLED emitters, these were classical fluorescent emitters. So electron and a hole would meet, they would form an exciton, so an excited state where we have two charges being localized on different units. And that excitonic state could then internally convert into a singlet excited state on the emitter, and that could fluoresce, emit a photon to the ground state. But in 25% of the cases, because of spin statistics, so there's only one singlet state and there's three triplet states when you have to spin half particles meet a hole and an electron. 75% of the energy that you put into it would end up in a triplet state, and that triplet state would be non-radiative because the spin rules in quantum mechanics dictate that you cannot change from a triplet to a singlet state. That's not entirely true. That's only true in a non-relativistic picture. So if you include relativity, then you will actually have coupling between singlet and triplet states through spin-orbit coupling. So we'd have spin-orbit coupled states. And the second generation of OLED emitters were phosphorescent emitters. These would typically be transition metal complexes, so heavy elements where relativistic effects play a larger role. They would have relatively large intersystem crossing rates. And so when the exciton would internally convert to a singlet state, it could rapidly intersystem cross through the spin-orbit coupling to a triplet state, and that triplet state could then also, again through spin-orbit coupling, phosphoresce to the ground state. So in developing these type of materials, typically you're looking at optimizing the spin-orbit coupling between the singlet and the triplet manifold, as well as from the triplet excited state, typically the T1 state, onto the singlet ground state. And so most OLED devices would still use that technology, depending on what type of colors, the pigments you have in them. And the third generation, and there's actually fourth generation, I don't have a picture on that, which is hyperfluorescence, again, makes use of that crossing between the two states. So you need to have some spin-orbit coupling, but rather than going from the singlet to the triplet state, it would go the other way around. So we would have our exciton giving rise to 25% singlet excited state, which could fluoresce directly, and 75% triplet state, which would be close in energy to the singlet state. And if there's enough energy, it could interconvert to the singlet state and then fluoresce. So since that is thermally activated and it's delayed fluorescence, that type of emission is called thermally activated delayed fluorescence, TADF. Okay, so let's say you want to make an OLED device. A lot of people have been using ADF to optimize these type of processes, but ideally you want to optimize the entire OLED stack simultaneously. So that is something that we're currently working towards. But first have a look at the emission properties. And so in 2005, Tom Ziegler, who I mentioned in the beginning, together with a few collaborators, implemented in our molecular DFT code time-dependent density functional theory, with which you can calculate excited state properties in combination with spin-orbit coupling. And so with this spin-orbit TDDFT, you can actually calculate the lifetime of a T1 state for emitting to the S0 state, or the T2 state or T3 state. But you can calculate the phosphorescent lifetimes of these triplet states. And so that was picked up by our neighbors in Germany, by BASF, who use this to screen materials to try and find an efficient blue emitter. So blue is the most energetic emission, and that's typically also the most difficult color to get right. But I picked up this spin-orbit coupling, TDDFT. Now they divested their portfolio, so all the patents have been sold to Universal Display. But it was interesting to see that they took up this academic development and knew how to use that to their advantage. And also in the early 2010s, DuPont was using this for screening their phosphorescent emitters, and they too have divested their portfolio. I think also to Universal Display. Around the same time, our Japanese resellers, so in certain countries we have partners who are typically also experts in using our software, made a case study where he studied something like 20 or so different complexes, where he compared this spin-orbit coupling TDDFT with the experimental results. And as you can see all across the range, typically you get pretty good predictions from this spin-orbit coupling TDDFT. So you can use that as a screening tool to quickly find what would be an emitter with a high lifetime, because you want a high lifetime. You want to make sure that once it's in the triplet state, it emits the photon, because otherwise you have a higher chance of getting non-radiative decay processes, which lead to worse conversion, and it also leads to potentially building up energy and breaking molecules and killing your pixels. Obviously, lifetime is important, but also the color. And so what's particularly important for very sharp OLED screens is that you have narrow emissions. And so here's an example for a platinum complex where actually the emission is not so narrow, it's rather broad. But you can calculate this vibrational broadening by using Frank Condon factor calculations. And as you can see, so in red, this is the calculated spectrum. And here is the measured spectrum at room temperature. So we use, of course, just simple Lorentzian broadening or Gaussian broadening. But you can see there's pretty good agreement in the color shape between the calculated and the measured spectra. So again, you can use that as a quick tool to screen the emission profile of your OLED emitter. These third generation of emitters, TADF, for them also this spin-orbit coupling is important, but typically more important is minimizing the gap between the singlet and the triplets, because it's a thermally activated process. The smaller the gap is, the higher the chance that you can reverse inter-system cross from the triplet to the singlet state. And there's also a range of complexes which were initially developed by Sonora, copper-based complexes, which also can phosphoresce. So then you get dual luminescence, so you get delayed fluorescence, regular fluorescence, and you get phosphorescence as well. And so you have three radiative pathways which you can optimize. As you can see also in the context, this was picked up first in academia. So there were Chinese groups, a group at Georgia Tech, and Jean-Luc Bledas, who were using these methods to predict the best type of TADF emitters. And later on, this was picked up by several companies as well. So by using these academic developments, the spin-orbit coupling, TDDFT, you can pragmatically use that to your advantage to get a better understanding of what kind of feature design you need to make the best TADF emitter. Now there's a recent class of these TADF emitters, the DEPNA. They typically have they have a boron atom centrally into nitrogen molecules. They tend to have very narrow emission profiles, and if you remember the range on the one I showed for the platinum, you can see indeed they are very narrow emitters here. And for these type of molecules, we're also building workflows to make the calculation much quicker. So since you need the excited state frequencies, they're typically quite expensive. So for a molecule like this, it would take around 28 hours on the 32 core machine. But by using different types of approximation, you can narrow it down to around half an hour. So you can do the calculation roughly 50 times as fast. So once we have the protocol set up, then it's very easy by using Python scripting to just modify a system. So you can change atoms for different groups of atoms, right? So you could change, for instance, a hydrogen atom here for a methyl group or something electron pushing or whatever. You run the optimization and then you calculate the emission spectrum with vibronic broadening. So there's a nice work unit for that. And this is then also very easy to push into the cloud, because then you can run on thousands of molecules simultaneously. You just need to have your workflow, define the type of ligand modifications that you want to do, and then just push it into the cloud, or if you have a large compute cluster, push it onto your cluster. Okay, so that is still quite an expensive game from a computational cost perspective, and that has to do with, as I mentioned, this forward versus inverse prediction. So classically, we build a molecule, ask for its properties, but by using machine learning techniques, we can do it the other way around. So rather than saying, okay, calculate all these molecules, what are the spectra, and then see which one has the best spectra, just put into the computer, this is the spectrum that I want. What would be the type of features on my molecule that would give rise to that spectrum? And so by training a machine learning model with these thousands of molecules, it can then autonomously design different types of molecules to give you the best spectrum that you have in mind. So there's a lot of activity going on in that area, and I see a much more future for these type of things. So yes, you'd still need a lot of calculations, but rather than running 1 million calculations, you can maybe get away with 1,000 calculations, put it into your machine learning model, and then maybe do 1,000 more to find your optimum desired property, in this case a spectrum, but it can be anything else as well, as long as it has a calculable property. Good. Yeah, so that's about emission properties. The other important property for these OLED devices is the mobility of the holes and the electrons. And again, there the story starts at the university. Sorry, let me take a quick sip. Where in 2003, there was a paper where people were interested in charge mobility in polymeric systems, and they found out that in ADF, because we use fragments as an input, you can define two different fragments and then calculate the molecule in that fragment basis, and the Fock matrix elements that you get out of that correspond to hopping events. So the HOMO corresponds to a hole hopping event, the LUMO corresponds to an electron hopping event. Again, that was picked up by our neighbors in Germany, by BASF, who then thought, okay, then this we can use for being able to predict the electron hole mobility in a range of organic semiconductor materials. And typically, let's say the accuracy is not that great as it was for predicting the phosphorescent lifetimes, but it is within 30%. So if you screen a large range of different materials, at least you can focus on maybe the top 30% rather than having to screen all the materials. Now, there's a little bit more advanced approach. I won't go into details, but you can also calculate these couplings from a adiabatic states, diagonalizing the 2x2 Hamiltonian in frozen density embedding approach. And that is a little bit more computationally expensive, but it allows you also to calculate a lot of other interesting properties. as well as include the environment effects. Yeah, okay, so then these are neat organic crystals. So again, bears have realized that, yeah, if we are going to make these layers in our device stack, obviously we cannot have crystalline material. So we have some deposition process. And so 1 year later from the paper that I mentioned, they did another paper where they use a Monte Carlo based approach, basin hopping, to deposit these molecules and then take pairs of molecules out of this disordered crystal and calculate the mobility, calculate the transfer integrals, do some integration over those mobilities to get the total mobility in the different directions. And as you can see, so here, for instance, the hopping rate in a crystalline material is typically much larger than it is in a disordered material, and there's typically a sort of a spread of different mobilities. But as you can see, the peak of the Gaussian is not exactly at the height of the mobility you would get in an ideal crystalline material. So it's good to know a little bit what the morphology does to your charge mobility, but also to other properties like exciton binding, exciton coupling, and emission properties. So what we've recently done is implement our own deposition method, which is essentially based on a feature that we use for things like chemical vapor deposition, etching, these kind of things. It's called the molecule gun. And it can be used in combination with an acceleration technique called force-biased Monte Carlo. And that setup can be used with anything that gives you forces and energy. So you can use it with force fields, but if you don't have an accurate enough force field, you can potentially run it also with electronic structure methods. So you could run it, for instance, with density functional base type binding. So here's an example of what that would look like. You need something that it could deposit on. In this case, we've chosen graphene, but it can be anything else. At some stage, it will fill up enough that you can freeze the bottom layers, and then it doesn't really matter anymore, and you probably throw away graphene in the first deposition layer. So in this case, we're using a universal force field with special parameters for the central copper atom, so UFF for MOF. Takes around 3 hours on a simple computer because it doesn't really parallelize well per each simulation. Of course, you can run many of these simulations. Takes around 3 hours for a total of 1.35 nanosecond simulation in this accelerated hypertime. So once then you have your deposition box, you can start picking, for instance, different dimers to calculate the mobility or of charges or of excitons, or you can pick a central one and calculate all the others with a polarizable force field to look at the excitation, the de-excitation properties. Okay, and then we're currently working with a company in the Netherlands called Symbiont. And Symbiont are a spin-off from Technical University in Eindhoven. The CTO did a PhD with Philips when they were still actively developing their OLED materials. So he knows a lot about the chemistry and the device level physics. And the goal, together with them, is to have an end-to-end prediction module from molecule to the device level to give the full output at the device level by using only atomistic simulations at the start in a single platform way. And there are a number of physical processes that they put in their kinetic Monte Carlo method for their device modeling. And so all the relevant electronic processes are there, all the relevant excitonic processes are there, as well as the degradation processes. Of course, this kinetic Monte Carlo, it just needs rates. It's very agnostic as to where it gets the rates from. So it can be experimental, it can be computed rates, it can be a combination of both, and eventually it can even be machine learned rates that uses a combination of both experimental and computed data. So the idea is then, okay, you build your OLED stack. So you have your whole transport layer, your electron transport layer, your injection layers, and your emission layer. And then for each one of these, you define your molecules, you do the deposition, as we just saw, and then calculate the relevant properties for that layer. Or if you don't, if we cannot calculate them for some reason, we can input experimental parameters as well, or guess them based on perhaps database values, and then do the full kinetic Monte Carlo calculation on the device level. And with that approach, you get all the relevant properties that you want to know if you're making a new device. So you get the device lifetime out of that, you get the color profile, you get the point shifts, you get the IV characteristics, the efficiency roll-off. So it's really nice to think about being able to then design a device that has, for instance, a better color profile or a longer device lifetime by ultimately designing new molecules at the atomistic level. Then also into play, as I mentioned, comes this machine learning or materials informatics in the context of machine learning, where you can use these new techniques, which are becoming better and better, to even make your screening more efficient. So there are several ways in which that can materialize. So a lot of effort is going in just training atomistic methods, right? So there's machine learned potentials, but there's also machine learned density functional approximations or machine learned optical properties. So as long as you have a data set, you can build a machine learned model on top of that. If you have some way to pass on the descriptor, right? So a smile string or something else that gives you the molecule or the materials information as an input for the machine learning model. And so those kind of methods can help you considerably increase the speed of the calculation and or the accuracy. So let's say, for instance, I want to do density functional theory calculations on a million molecules. That's going to be pretty expensive, but if I could do them at the DFTB level, that's going to be 1,000 times as fast. But if I can now train these DFTB parameters to be as good as a DFT, then I've gained so much in compute time, but lost nothing in accuracy. If I can even then do some reinforcement learning and maybe sort of train to higher level methods like GW, I could even build a machine learning model that gives me higher accuracy than a DFT calculation. So yeah, there's going to be a lot of things happening in this area in the next decade, and of course we try to be involved in that in the context of enabling our researchers to use that to their advantage. I already mentioned this inverse design. So yeah, encode property to a certain structure. So rather than forward doing inverse prediction, and that's particularly well suited for this problem of optimizing an OLED device, because there we have multiple materials, and for each one of these materials we need to optimize not only one but usually a couple of properties. So multi-property, multi-materials optimization, that becomes increasingly difficult to optimize from a combinatorial point of view, but these machine learned models, they have no problem, of course, with such high dimensionality, and in particular these inverse design principles where you have, let's say, one or two properties that you're interested in, can just through the machine learning neural networks work out in the end what would be the ideal set of molecules that gives rise to that ultimate property or set of properties that you're interested in. Experimental input can be used in all of these methods because we can calculate all that we want, but in the end, if the material has a different property or the material cannot be made, then that's useless. So there always needs to be a synergy between experiment and computations, and we can use that to our advantage, specifically in the context of machine learning, because we can then exactly get the properties that we measure in the lab and use that as an input parameter, training parameter for machine learning models. And there's a bunch of future developments down the line. You may have seen these robots that run around the lab, especially in the COVID time. They can just be steered from your computer and just say, okay, go and make these molecules, measure them, and so on. And so that is a pretty cool development. And I think in combination with running these machine learned computational experiments, that can be really, really powerful. So in a nutshell, this is then what we envision. So we have millions of candidates, but we cannot run millions of candidates at a DFT level on a day-to-day level. So we need some machine learning, deep learning to train a model to find the molecules that are the most relevant to calculate, maybe improve even the density functional approximations, and then finally at the bottom of the pipeline end up with a few candidates. And then the extra loop on top of that is going to be the multi-scale modeling in this Bumblebee setup with the Dutch company Symbiont. So ultimately we want to, as the ultimate output, we want to have the device level properties that we want to trace all the way back to the most relevant molecules. Let me have a look at how we are for time. Maybe just very quickly tell you a little bit about the other type of materials that we're working on, also in the context of generating a platform that ideally allows you to put things in the cloud and go to multi-scale modeling. And let's have a look at batteries, polymers, and catalysis very briefly. So for battery modeling, there are a range of different properties that, again, you'd want to optimize. Let's focus on a few which are coming from ReaxFF simulation. So ReaxFF is a reactive molecular force field that allows you to study large complex systems where you have bond breaking and bond formation. Originally it was developed for combustion chemistry, but it's finding more and more diverse applications, and one of which is batteries, another one is polymers. So I have a couple of ReaxFF applications for polymers as well. Now, by using ReaxFF, you can again do this computer experiment, so you can get an understanding, for instance, in what's happening in a sulfur anode during the discharge process, or you can have a look at what's happening during the discharge with the electrolyte. And there's a couple of examples on that. I hope I have a video on this. Let's see if this works. So when you start to discharge your lithium, your classical lithium ion, lithium sulfur battery, the lithium starts to intercalate into the sulfur electrode, and that leads to stress. And you can model this by doing grand canonical Monte Carlo simulations with ReaxFF. And then you can start to see during the discharge process, you can see the expansion, and you can also see the reduction of the chemical potential that corresponds to a reduction in the voltage. So let's see what that looks like. So in the beginning, we have still a high voltage in the battery as we start putting in more lithium ions into the sulfur cathode. The cathode starts to expand. It becomes increasingly more difficult to put in more lithium. So it's very difficult to get to a lithium sulfur ratio of 2 before the battery dies. And then we just need to reverse the process to recharge it. So that is just useful that also to think about modifying these cathodes to think about having a higher capacity for lithium uptake without the voltage dropping too much. Okay, somehow I'm out of my presentation. Let's quickly go back to where we were. Right, so also in the context of batteries, we are moving towards larger scale modeling. So we're collaborating with Wasatch Molecular, who develop polarizable force fields, which are useful for large scale mobility calculations of fuel cells and batteries. But it cannot take account of the actual reactive event. So for that, we need to zoom in on ReactFF. And on the higher end scale, they're also working on coarse grained methods, so you can go to mesoscale modeling of these battery devices. So that is the end goal with Wasatch. So working on that for battery modeling. And again, of course, since you need to run a lot of these simulations, they're quite amenable for deploying that on a cloud-based environment as well as on a classical Linux cluster. Similarly for polymers, there are a lot of different things you can do in the Amsterdam modeling suite. Traditionally, I mentioned these chemical companies. They were really interested in using ADF to understand the polymerization catalyst, so Ziegler-Natta catalyst. People still using it for that aspect. So understanding reaction barriers, how do you tweak the catalyst to get a higher turnover frequency? And more recently, we have a number of interesting applications using ReactFF, where you can study, for instance, cross-linking reactions and then look at the cross-linked polymers and try and understand their mechanical properties, as well as degradation properties. And there are also a couple of interesting applications, but this is a little bit tougher for the nonlinear optical properties of these polymers in the context of using them for 5G and 6G applications. So you can use a periodic DFT code band to do time-dependent current density functional theory, or you can use MD together with the polarizable force fields to get some of the relevant optical properties for those type of applications. Right, so yeah, in a nutshell, this polymer formation is a very old idea from the 80s called bond tracking. Essentially, you just say, okay, let the molecules just find each other, but if they're somehow in a pre-transition state configuration, let's give them a little boost, push them a little bit closer to the transition state, and that allows you to run these cross-linking simulations in a time scale of a couple of hours rather than a couple of days. So literally on the same time scale as you would do the cross-linking experiments in the lab. And typically what you get out of that are pretty good cross-linking densities, and also the mechanical properties, things like glass transition temperatures are pretty good. So you can use these simulations, these bond tracking or bond boost simulations, to design different curing agents to get, for instance, higher densities or polymers with higher glass transition temperatures. So you can see that the trends between the experiments and the simulations are in excellent agreement. There's one property that isn't so well calculated, which is the coefficient of thermal expansion. So there, these simulations don't give much predictive value at all. It's probably understood why it is, but it requires reparameterization of the reactive force field. So that is something you can do, but it depends on whether that's a useful property for the kind of applications that you would want to use these polymers for. And finally, just as a fun example, if you want to make polymers for spacecrafts, you want to make sure that they're very resilient. So you can think about designing polymers that don't really erode when you hit them with high velocity oxygen atoms as a proxy for the conditions in low Earth orbit. And so I thought that was quite a nice application where you just look at reactive molecular dynamics to see what type of polymers are the most resilient under these conditions. Finally, this thermodynamic calculations with Cosmos, continuous solvation model for realistic solvents. That allows you to screen, for instance, how can you mix different sets of polymers, and so that has applications in, for instance, organic electronics as well. So you could think about what would be a good polymer blend for the type of materials that you have in mind before you actually go and run the atomistic simulations with the deposition that I just showed. Yeah, then in terms of classical chemical reactivity, if you will, we are currently trying to put together all the length scales that allow you to model a chemical reactor at the reactor scale. So you can run the computational fluid dynamics where you have your reactants coming in, you have your products coming out, you take into account all the dynamics. you go one scale beyond that, then we look at the mesoscale of these catalytic pellets. So we need to define their morphology, and then on this morphology, we need to define the reactivity, which comes from a lower mesoscale method, typically kinetic Monte Carlo or microkinetics. And the rates in these microkinetics or kinetic Monte Carlo then come from electron extraction methods. So in our case, that would be DFT. For that to happen, we also need automated tools to get reaction pathways. And so there's different ways that you can do it. So for instance, in Korea at KAIST, there's a group actively developing these graph-based methods, ACE reaction, which is really neat. It does work with our software, but we still need to make a user interface around it. But these are the kind of things that are also typically very amenable to put onto the cloud, because you need to do many different calculations, relatively small calculations, and then gather the results in the end. And so if you have these automated reaction pathways, then it's easy to input them into kinetic Monte Carlo. There's also adaptive kinetic Monte Carlo that does that automatically, but maybe you want to first have a look at the reaction network first, and then couple that into the computational fluid dynamics for the full reactor scale modeling. So in this coupling, you need to couple all scales, so length and time scales, iteratively. So that's quite a difficult process, because you need to understand input and output and sensitivity of each one of these models. So that's still work in progress, but we're at least getting to the first stage of this, and then hopefully we'll be able to extend it in next.
Hello? Pedro, can you hear me?
Yeah, sorry. Yeah.
Oh, yeah. Sorry, I thought I had lost you for a couple of seconds. Okay, yeah, so thank you very much for your very insightful presentation on SCM and applications and software solutions. So at this point, yeah, I propose you take a look at the Q&A section, although you can see that there are no questions at the moment.
No, I don't see any questions. Yeah.
Okay, so of course I invite all participants to please propose any questions that they might think of. I propose to wait maybe a couple of minutes to allow everyone to take the time to think about any possible questions. So in case there are no questions, maybe I can ask you very briefly about, in very general terms, I mean, I see that you have a lot of very large industrial collaborations going on. So I saw the names of BASF before and other large industrial groups. So in general, how optimistic are you in terms of the interest of large chemical companies in investing in computational chemistry and, for example, DFT solutions in the future? Do you think this is a sector of R&D which is destined to grow and to attract more and more interest? Or
yeah,
just wanted to ask your very general opinions about this.
That's a good question. So you would think that, for instance, so last year's COVID problems would lead to a lot of problems, right? Because people have less budgets, and to a certain extent this is true, and especially, of course, in the petrochemical industry. So we did see a little bit drop in demand there, but yeah, they typically the people who are in the bigger chemical and petrochemical companies, as well as in the electronic companies, they have a long background in chemistry and physics modeling, and they know that it can bring value. So yeah, I don't see any reason why this is going to diminish. From my understanding is that the growth at the atomistic modeling is roughly around 7 to 8% per year. And if you go to the mesoscale modeling, right? So the computer-aided engineering, and you probably know more about that from your work at the EMMC with Garrett Goldbeck. That is growing even faster, and the reason is, let's say, the closer you are to actually getting a new device or a new actual item into production, the more costly it is to waste time. So then it makes sense to put in a lot of resources in the modeling to cut down the production time for the actual innovation. And so we see still quite a lot of people using it at the early discovery stage, but more and more also using atomistic modeling to use it at the end stage, and that is more common, let's say, in people who do process engineering, and that can be again in the chemical space as well as the pharmaceutical space, for instance. Whereas if you think about like applications in OLED materials and batteries, there I think having something that, so what we want to make, having something that gives you end-to-end solution, that is going to be something that people would be really interested in to use. Because currently there are different groups that do different research areas, and if you can provide them with a central tool for which everybody can understand their part, and everybody can agree on the useful outcome, that is quite valuable. So I hope that answers your question a bit.
Oh yeah, certainly. Yeah, thank you very much. Yeah, so I also share, I mean, part of your optimism. I mean, I personally, I come more from the world of so material science simulations, which of course, I mean, has a lot of crossover with computational chemistry. But in fact, I mean, I can testify that over the last, say, 5 or 6 years, I've seen also a very rapid increase in the amount of, say, industrial interest in this field. And simply counting also the number of startups which have emerged, focusing on, for example, either machine learning-based material informatics applications or even directly DFT-based simulations. I've seen quite a noticeable increase. So it looks like this is still a good time to be a computational chemist or material scientist.
No, absolutely.
Opportunities.
And there's definitely, let's say, room for having solutions which are more easily accessible, especially if you can offer some consulting on the side on the science, because the smaller companies typically they have maybe one person who knows a little bit about materials modeling or computational chemistry, but they have a lot of other things to do. They don't have somebody who can run the administration on the cluster if they want to run there. So having something that's easily accessible from a web interface, that is definitely useful for them, because they also know that through modeling they can reduce the experimental wasteful experiments, right? So they can reduce the wasteful experiments by zooming in on the ones that are most useful. But they don't have the time or they don't want to build up the expertise and the infrastructure for running this. So I definitely see that there's going to be a growth in having web-based solutions for this.
Oh yeah, certainly, yeah. And in fact, I mean, this is seems to be a common pattern nowadays to try to move everything in, at least the most solutions in the form of software as a service platforms. And it's also interesting to notice that, so we mentioned the increase in the number of startup companies emerging in this field. I think, I mean, I try to list many of them on my website, but I mean, some noticeable example would be, of course, the Citrine Informatics, which is a startup which is going very rapidly in San Francisco area. And But and it's also interesting to notice how more and more you see in this startups environment, you see scientists working very well along, for example, computer scientists. So you typically have computer scientists, so people with a pure programming background working hand in hand with people with a science background, and then now also people with a business background. And so it's the synergy seems to be working more.
No, absolutely. Yeah, and so I understood you are collaborating with Metmorize, right? And that's also, so they're a spin-off from Georgia Tech, and so there's also a mixture of domain experts, good computational scientists, and business people. So indeed, it seems a good combination. And so the other thing is that, for teaching, as we've seen this year, having something that people can run from their computer at home is very useful as well. And so we did a virtual workshop February 2020 before we didn't have a problem here in Europe yet with this COVID. And then the organizer asked, can we make like a paper for this for the Journal of Chemical Education, because apparently there's not so much literature on this, on using virtual labs from the computer for actual teaching, and of course having something that's easily deployed again from the web, that is very useful.
Certainly, yeah. Actually, by the way, I just noticed now that there is someone who asked a question, but actually more and more questions have appeared in the Q&A.
Okay, I see.
So you can maybe take a look. And,
okay, so could you please expand a bit on bottlenecks in designing OLED materials? So I'll answer that live. So it depends a little bit on who you talk to, right? So if you have the people who do the full vertical integration, they need to get everything right. So they need to get the right color, they need to get the right lifetime, they need to get the right stability. And so my limited understanding is that it's very difficult to get all three of these right, but still the most difficult problem is to get a good blue emitter that has a narrow emission range, which is also very stable to the extent that it won't easily follow non-radiative degradation pathways. And I think that's still one of the challenges which is currently being chased by a lot of different companies. They have a lot of companies who make the materials and they just deliver them, and then they focus each on their own problem, right? So it needs to have a certain mobility range or something like that. But I think for the OLEDs, at least from a molecular design perspective, finding a good blue emitter is still one of the things that people are currently chasing. So I hope that answers that question. It's not the definitive answer because I'm not the legal expert in that area, but that is my understanding at least. So the question is, next question is, I wondered if CosmRS can be applied for designing a piezoelectric polymer. So I'll answer that one also live. No, not so much. So this CosmRS is, in a nutshell, what it does, it calculates pseudo-activity coefficients based on surface charges. So these surface charges you calculate from a molecule in a perfect conductor, and you bin them in a histogram. So you got a bunch of positive, bunch of negatives, and then you try and mix everything together in the mixture of your choice. So then you let all the positive and the negative charges interact with each other, positives with the positives, and from that you get the thermodynamic properties. So you get the excess mixing energy, but you don't get any other type of properties out of that. So if you want piezoelectricity, then you need to calculate that at the electronic structure level itself. So I hope that answers that question. All
right, I can see there are no more questions in the Q&A section. So yeah, with that, I therefore propose that we move on into our next presentation. So thank you very much again.
Oh, thank you for organizing this.
Yeah, for your very insightful presentation. Actually, now that I just finished speaking, I can see there are another couple of questions which just popped up in the Q&A. So
I could still take them if there's time.
Yeah. So if you still have time.
Yeah, sure. So let's look at Christian's question. So what advantages this? I was talking, but you couldn't hear me. So sorry.
Yeah, so you were muted for a couple of seconds.
Yeah. So so the question from Christian, where is it? Yeah. So what are the advantages of materials discovery from passing to larger scales? And so the advantages are that, let's say in the context of OLED, I could make an OLED emitter that has the right color, that has the right lifetime. But then if I put it into my host material, it could be that there's a misalignment of the energy level. So the exciton cannot reach my OLED emitter. So you need to take into account the whole picture. Also then, for instance, if you then put it in an entire stack, it could be that there's also a misalignment between the levels of the Hall and the electron transport layer and the emission layer. So ultimately for the design for OLEDs, you need to take into account the whole picture. If you think about catalysis, it's the same, right? So I can design, for instance, a new catalyst that has a really high turnover frequency for the reaction of interest, but it could also be that in my full reactor scale modeling, that the reactants will not reach my catalyst and it will do other types of reactions, which I can input into this mesoscale modeling. So ultimately, ideally, you'd want to model the full physics, but we're just focusing currently on the atomistic methods, pass those on to the mesoscale methods so you can do the full scale modeling. So Christian, I hope that answers your question, at least my view on that. Yeah, and I think, okay, so the other two aren't really questions, so thank you. Well, thank you for attention. So Gabriela, do we have, did I miss anything?
No, I think you have successfully answered everything. Thank you very much again for your availability today and for your for all the information that you could provide us. So at this stage, yeah, I therefore propose that we move on into our next and final presentation. So the final presentation for not just for today's workshop, but for the whole series of events, considering that today is our final day. And our next speaker will be Dr. Curtis Stockbrough. But before I introduce him, I just wanted to receive confirmation from my colleagues at Virtual Park that he has indeed successfully joined the workshop. That is currently available to present. So maybe Minkyu, can you please confirm that he has joined the event?
Yeah, I think it's kind of a 10 minutes break for the next presentation because he waiting for the next presentation. So we have left 5 minutes for the break or 5 or 10 minute break, and then I'm waiting for the next presentations. It's gonna be better.
Okay, that's understandable. Okay, now, in fact, we are running a little bit earlier on schedule. So as Minkyu said, I propose that we have a 5 to 10 minutes break now, and that we resume our workshop as soon as Dr. Stockbrough will have joined us. So in about 10 minutes time, hopefully slightly sooner. But I will let you know as soon as we are ready to start our next final presentation. So yeah, please stay connected for the moment.
Also, you guys, you have any question, just feel free to asking for any question for the simulations or some material scale or some SCM company. So please feel free to give some question for the break time.
안녕하세요. 저는 버추얼랩 대표 이민호라고 합니다. 버추얼랩은 2016년도에 키스트, 그러니까 한국과학기술연구원의 계산과학연구센터에서 스핀오프한 스타트업이고요. 그리고 소재 분야를 시작으로 해서 클라우드 기반의 R&D 환경을 만들어가고 있습니다. 저희 회사에서는 머티리얼 스퀘어라는 서비스를 운영 중인데요. 소재 연구 개발을 하시는 연구자분들이 빅데이터나 시뮬레이션, 기계학습과 같은 IT 기반의 기술들을 손쉽게 활용하실 수 있도록 해드리는 플랫폼입니다. 신소재 개발에는 시뮬레이션이 많이 사용이 되는데 그 이유가 신소재 개발이라는 프로세스 자체가 비용과 시간이 많이 들어갑니다. 시뮬레이션을 도입을 한다라고 하면은 슈퍼컴퓨터도 직접 사야 되고요. 어려운 코드도 설치를 해야 되고
All right. Sorry, I just wanted to inform the audience that so I had a very quick interaction with Dr. Stockrow, and he said he should be able to join us very soon. And he apologizes for a small delay, but he had an inconvenience, a last-minute inconvenience. So we just need to wait, I think, a few minutes, and he should be ready to join us and give his presentation. Right. Sorry, I just wanted to inform the audience that I had a quick phone call with Dr. Stockbro, and he's experiencing some technical problems with his internet connection and his computer in general. So, but he promised me that he should be able to still join the workshop in a couple of minutes' time, the time to reboot his computer and everything. So I invite you to please be patient and wait another couple of minutes, and we should still have time for his presentation. Again, I would like to apologize for this inconvenience and for this delay. And thank you very much again for your patience.
All right, this is Minkyu Park from Virtual Lab. I'm really sorry for the inconvenience for the technical issue for the Zoom. So I'll give you a very short introduction for the materials care for the open research here. Actually, we are pursued for the open research like FAIR DI in EU area or some new materials project in the US area. So we are make a open research tab in here. So when you use the materials care, you can share your researches in this field. So you can click the open research and open research and open research click the here, and you can find the quantum espresso and games and lamps Calpad. And also we have many events for here, follow me contest or something like that. So for instance, today I have introduced for the phonon calculation. And so you have, if you are interested in the phonon calculation, you can find the open research in here. For example, here, this is here, you can press see data for the today's workshop for the virtual lab. And you can press the see data here, you can loading your work. So actually, this is this calculation from the anonymous in the materials care users, and you can publish your results in the by using the open research here. Okay, so today I was introduced for the phonon calculation of silicon materials, and you can check the details up here. So if you're interested in the input script or the quantum express for the phonon calculation, and you can check for the input script here and the potentials, which is we have used the PV functionals are here. And also, so phonon calculation quite difficult to calculate for the in the field of the theoretical calculations. So, just a second. All right. So it's ready for the next workshop, which is the last workshop. So I just want to pass through the stock programs. All right. Thank you so much.
Yes, hello.
Yes.
Yes, I hope that I will not have further problems with my computer today. So
all right.
At least it's working right now. So
it's perfect. All right.
Okay, good. Yeah. So sorry for the delay. So let me share my screen. Can you see my screen now?
Yeah, I can see you perfectly. All right, thank you so much.
Can you see the presentation?
Yeah, we can see it perfectly well. You can start, yeah.
Okay. Yes, my name is Kurt Stockbro, and I'll tell you kind of my story, what I have been doing in my professional life, working first as I have a PhD in computational physics from the Danish Technical University, and then I took the kind of academic track, first a postdoc and then associate professor, and then I decided to make some startups, and I made two startups, one Atomistics back in 2003, and what is shown here is the number of employees. So you can see in Atomistics it grew very fast from 0 to 60 people, but then you can see also actually it went down again quite fast. So something interesting happened here. And then the orange one is my other company that I started afterwards, QuantumWise, and you can see that in this case it was a different kind of growth. So so I will tell you my story about how I started these companies, and in the second case I sold off the company to Synopsys. So I will tell you a little about this process, and today I work as a tech investor, so I will also tell you a little about my life today. So how long time, when should I finish? So how long time do I have? Just to let me know.
Sorry. I think you can go until 9 o'clock.
Okay, yeah. So the agenda. So first of all, I'll tell you a little about why did I care to make a spin out, and why didn't I stay in academia and try to kind of commercialize my research. Then I'll tell you the story about Atomistics and QuantumWise, and how I sold my company, and now my life as a tech investor. So you can say it's some part of my life story. I told in the beginning a little about my professional career. I have a PhD in computational physics from the Technical University. Then I went as a postdoc, worked on electronic structure methods. Actually, I worked on the quantum espresso code in Trieste, implemented different parts on that, and came back to DTU, where I became an associate professor. And there we got a project on how to calculate electrical currents in molecular systems. So at that time, there was a lot of interest in that you could use maybe molecules as as a computer, as a transistor. And then we were interested in, could you theoretically calculate the electrical properties of a molecule? And there were no good methods for doing that at this time. So I wanted where you, from first principles, could calculate IV curves. And so we wanted to base this on density functional theory, but at that time you had codes that could simulate the electronic properties of molecules or of periodic systems, but such a molecular device, it's actually a combination of the two, because you have a periodic system and coming in, for instance, from the left, and then you have a molecule, and then it goes out to the right again. So it's not really either an isolated system or periodic system. It's a kind of molecule with semi-periodic or with semi-infinite leads. So this was a new type of system, and so we wanted to extend density functional theory to simulate this type of systems. So I hired a postdoc, Mads Brandby, and actually he have done some work on tight binding using Green's function methods, and he said that he believed that non-equilibrium Green functions could actually tackle this kind of a problem. And so he have used the non-equilibrium Green function for tight binding models, but we really wanted to do it on DFT methods. So we were looking for a DFT method that also had a tight binding that was described at the tight binding level. So we looked around, and we saw that this at this time there was the Siesta code has just been developed, and this looked very promising. So I called Pablo Orion in Barcelona, and he thought it was a very interesting problem, and actually he have hired a postdoc to tackle the same problem. So we decided that we would combine forces and try to develop a transport method on top of the Siesta code. So this came to be what was called the Trans-Siesta method. So and we published that in 2002 in PRB, and actually this paper has been selected as one of the 50 most important papers of PRB here at the 50 years anniversary. So you can see the authors. I mean, it's me, and it's Mads, and then it's Pablo Orion, and then there's also his postdoc, Jose Luis Mozos. But you can see there's also a fifth person, Jeremy Taylor. So actually, that's also an interesting story how Jeremy came on board, because we have worked on this method, and we had the DFT code from Spain, and actually Mads have worked on non-equilibrium Green functions, and we also had locally at DTU a professor, Hans Skriver, who have worked on one of the technical things that were important was to use complex contours for the integration. So it turned out that people that have tried this before have and it's not really numerically feasible. So for it to be feasible, you need to go out in the complex plane and do this integration in the complex plane. And we work with this professor, Hans Skriver, and he teaches us how to do that. And that was one of the important things in actually getting this to work. But then suddenly my boss, Antti-Pekka Jauho, he came and said, oh, there's, I know a professor in Canada, Hongu, and he has a PhD student that would like to come to Denmark and do a postdoc, and actually he has his own salary. And it seems that he's doing something similar as to what you and Mads is doing. And okay, we got quite interested, and we saw the letter from Hongu, and Mads said, "Oh, this must be Jesus," because it was actually quite amazing what Jeremy had been doing in the group of Hongu, because he have both developed the DFT tight binding method, but he has also developed the transport method, and he has also figured out how to do these complex contours. His contours were not as advanced as those Mads and I were using, because we have worked with this professor, but I mean, he actually have found out all the right pieces similar to what we have found. So, and it turned out that the reason he wanted to come to Denmark was that his wife is Danish, and he wanted to come together in Denmark with his girlfriend at that point, which he had met in Canada. So so Jeremy became a part of the group, and we have actually done. We were almost